So, hello everybody, let's start the keynote. I'm Dmitry Petrashko. I'm here to present you my experience in adventures in efficiency and performance. I would like us to have this adventure together to follow through some of the interesting things that I discovered while working on either on different areas of performance in Scala. So, just to introduce myself, I'm Dmitry. I've just recently defended a PhD on Dotty design and architecture. I'm the first one to graduate on Dotty. Okay. Thank you. Yeah, so before I started designing Dotty with Martin, I actually worked on Scala Blitz. And Scala Blitz were parallel collections for Scala, which were macro-generated, and the API designs there influenced the design of the new Scala collections. And I started the .linker and optimizer project, which will be carried on by the next generations of students at EPFL. So now I'm with Stripe. I'm working on something very exciting, which I unfortunately can't yet disclose. But it's going to be really interesting, so stay tuned. Okay, so in my title slide, I had efficiency and performance, which means I separate the two. So let's start from here and let's try to make a dialogue with you as the audience. Does anybody know what's the difference between efficiency and performance? So let's start with efficiency. Okay, efficiency means doing less work. There are multiple ways you can do less work. Either you can be smart about what work you're doing and use a more efficient algorithm which does less steps, or you can simply not do something. So when we're talking about an efficient algorithm, that's an algorithm which, for this specific task, will use the minimal amount of steps needed to get this task done. Well, there's a difference with performance because we're talking about some abstract steps. Performance is more practical. Performance means doing it faster. Doing it faster may entail making the steps take shorter amount of time or making those steps somehow fused with each other. Though it doesn't fundamentally change the algorithm, it doesn't fundamentally change efficiency, it contributes to our experience. If you have an efficient algorithm which is implemented badly, it's not performant, it may take forever to finish because there is a huge constant in front of it. So now, the only way you can know performance in practice is to know your hardware. Most of this talk is going to be about both performance and efficiency, so some of it is going to include knowledge about hardware. And any moment if you see that you're not following, please yell at me and ask me to explain you. Now, let our adventures begin. Most of these experiences are about me breaking my assumptions. Most of the things taught me something that I assumed was true is actually false. And I'll be glad if some people of the audience will help me to share if they had similar experiences. So first one, can an efficient algorithm be actually more performant? Are there some cases where you will decide to intentionally use an algorithm which is inefficient because it's faster? Yes. Examples? Sorting. Yes, that's a wonderful example. Insertion sort for small arrays is faster than quicksort. Well, the tricky part here is define small. Define small here is 5,000 elements. So it's even more funny given that for most applications, average array size is under 4 elements. In practice, a lot of standard libraries do something funny. They check how many elements are you going to sort and use different algorithms. For example, C++ standard library actually has 3 algorithms implemented. It starts with a quick sort. If it sees that data is big, if it sees the quick sort takes too much steps, it decides it will just bail out and go merge sort, because maybe it's a worst case of squeeze sort. And if the data is small, it's going to do insertion sort. So why is that? So for those who are trying to figure out why this happens, well, if you follow the algorithm class, you have these formulas, which say, the number of operation it takes for quicksort to succeed is an average n log n. Well, there's actually a constant here. When you're talking about algorithms in the algorithms class, you disregard the constants. Well, the constants matter, because if your constant is years, if it takes you, centuries to finish it, it doesn't matter if it scales well. You're not going to survive till it finishes sort in the small array. Insertion sort instead has a very small constant multiplier, which if the n is really small, the constant multiplier matters a lot more than the size of an array. Okay, the next one. Can doing more work be actually faster than doing less work? Any examples from experience? So far, let's say we're doing everything in single thread. Pipelining is interesting, but can you give me an example where you literally just do something extra, which wouldn't make it presumably faster? So that's a very tricky example that I recently learned. Let's say that I do a more specific question, because I think it's very unlikely for people to just spot this out right. Can a 64-byte write be faster than 1-byte write? Why? Let's say we're only doing memory. So we're only doing arrays here, something in memory. Okay, so it has to be aligned. And what happens if 64-byte write is aligned? Yes. Yeah. So the thing is, when you work with memory, though you look like you work with integers and bytes and booleans, the CPU works in lines of memory. And the line is 64 bytes. So let's say you want to write 1 byte. What does CPU have to do if the only thing it can do is write 64 bytes? It's going to go, read the entire line, change 1 byte that you changed, and write the entire line. If you were to actually write all 64 bytes, write more, it will need to do the read. It will just rewrite everything which it already has in memory. In practice, it means that you don't have a blocking operation here. It doesn't stall the pipeline. Doing this trick makes it a lot faster to do operations which are very write intensive. So let's say if you have an object which has a lot of fields, it may make sense to add more fields to it and just write zeros into it, because it will become faster to write a single field that you care about. If you want to look how this is done, have a look at LMAX Disruptor. They were very careful about it and they did it really nice. It also ensures that if you're in a multi-threaded environment, you don't have conflicts with other threads. Because, if the other thread also owns the line, you don't have to be careful about, synchronizing other parts of the line. Okay. Less instructions means faster code. The standard assumption. If you see a lot of code, maybe it's slow. If you see a small amount of code, it's fast. Any counterexamples from experience?
Loop unrolling.
Okay, loop unrolling. Any other?
Thread sleep 5000.
Okay. That's true. Vector instructions. That's nice. Well, this simple example is the one that I presented in the previous slide. The previous slide writes more. Okay. But in general, it's actually quite common. There are multiple examples when this happens. First of all, some instructions are simple, some instructions are hard. You can actually look up how long do instructions take. Some of the instructions literally take thousands of times of more than others. In particular, if you're using some kind of instructions which work on strings, then they take time proportional to the length of string, though that's a single instruction. But sometimes the CPU is simply weird. So this is going to be a single example from the entire talk that I did not find myself. I instead was invited to discussion. It was very interesting to figure it out. And unfortunately, this example is going to be in C. So this loop, the loop which just increases the counter, which has an ASM call inside. This ASM call calls a function which does nothing. Uncommenting this line substantially changes performance of this program. on Haswell, i7, not i5, not any other architecture. So uncommenting this line makes this code substantially faster in this specific case, like by 1/6, so like 16%. That's weird, to say the least. And it's quite common in hardware. In hardware, if you're working with benchmarking, if you're working with the real hardware, it's going to have internal hacks, which hardware developers use to make it fast. Sometimes you fall between the cracks. Here, well, we have speculation that this is due to loop alignment. Making this loop bigger makes it more likely for some of the optimizations inside the CPU to trigger. When the loop is small, they for some reason don't trigger. And, well, Intel will never disclose this because then they will kind of have to accept that they fucked up the cycles of one instruction. Yeah. Okay. Now, somebody discussed pipelining. Can a single-threaded program do work in parallel? Any examples from experience? Okay, single instruction, multiple data. But let's say you write normal Scala. You write normal Scala, you don't have any tricky instructions, you don't have any fancy stuff yet. We're trying to give it to you, but it's not there yet. If you write a single threaded program in Scala,
it's not possible in JVM. Just run it.
okay, that's the right answer. So first of all, I was expecting to hear the GC answer. So if you write something in Scala, it will always be parallel because GC is always parallel. But otherwise, there's instruction level parallelism. So let's consider this program. In the first instruction, in the first line here, we have this read of S. This read, if it goes to memory, it will take substantial amount of time. It will take thousands of instructions just to read this into single field. In order to make CPUs faster, what these hardware guys did is they started out-of-order execution and they started speculation. So in practice, what will happen is when you read this field, it will actually start executing the line below without waiting for it. It's able to see that you don't need this field to start doing this all arithmetics. And in practice, most of this instruction will finish before the read finishes execution. If you want to go into more details, that's a scheme of how Haswell works, and there's something called issue width, which is how many micro-ops it can execute at the same time. Haswell can, in parallel, schedule 8 micro-ops to be executed and to be retired. Which means that even if you write a single-threaded program, if you write it carefully and make sure that the CPU can use all of it, you can also have it executed in parallel. In practice, this means that the well-written single-threaded program can be up to 4 to 5 times faster than the poorly written one. In the last slides, I'll show you some things that you should keep in mind to take advantage of that thing. But I believe that that's the thing which shows the most experienced programmer, which knows how to write the code that not only people can understand it, but the hardware can also do it. Okay, the fun stuff and the harder stuff. So the CPU does a lot of speculations. Can failed speculations be good? Otherwise, the question wouldn't be there. So the example actually comes from Hydra. Hydra is a variation of compiler which is developed by Yulian Dragos and Triple Quote, and they've sent me a very funny measurements, and they were seeing that in case hyper-threading is disabled, they have huge amount of speculation failures. And here's a slide which explains why. Again, we have an instruction which takes a lot of time to execute. We have a memory read, and then we have a branch. If you're smart, what will you do? Yes. So what the CPU does, and that's what actually happens if you do pattern matching in Scala. Pattern matching in Scala is compiled into comparisons on integers. And that's why on contemporary VMs, on contemporary hardware, reordering instance of checks doesn't matter because they all happen at the same time. The CPU executes all of them in parallel and then figure out which ones it didn't have to execute and doesn't retire them. That's an interesting thing. If you're doing low-level hardware profiling, you can have some stuff which normally is assumed to be really bad, as in failed speculation. CPU tried to do something efficiently and it wasn't. Well, sometimes it's good. Sometimes the CPU just does more stuff to make it faster. Okay. Now, with entire my talk, there is one one thing to make a note. The date makes a difference. All of the things that I'm explaining are valid today. They may be invalid tomorrow, and to show you how severe this is, I'll show you some graphs. Those are some specific 3 measurements, which is L1 cache hit rate on the left, branch mispredict, and main memory reference. Normally, when the hardware guys show you these numbers, they show you them in cycles. What I did instead here, I showed you them in nanoseconds, which is the number that you actually experience. So when I was born in 1990, branch mispredict costed substantially more than the main memory reference, which meant that it was a viable strategy to optimize the code by storing more data in memory and caching in order not to have ifs. Because every time the CPU wasn't able to guess which branch of if you were doing, you could as well did 3 reads from memory. And a lot of software at the time was written with this recipe in mind. They were hand optimizing the code to store some data which will be then used homogeneously, as if instead of having one branch, it will use the same code which inside the data encodes 2 branches. Well, the hardware evolved. In 1991, the gap became smaller, and if you actually go up until 1994, they evened out. Starting in 1995, it was better to have branch mispredict than main memory reference. There is still a lot of old know-how on the internet and among the people who say that cache everything, don't do the ifs. It's deprecated by 20 years now. But people still tell this. And to be frank, there is still architecture where this makes sense. If you're coding for microcontrollers, maybe it does make sense. If you're coding in Scala, I guess you're not running under microcontrollers yet. So this red line shows a moment where a lot of know-how and a lot of programs, which before this were smart and written in the right way, should have been started to be rewritten because the assumptions under which they were written no longer hold. And as you could expect, it became worse with every year. The main memory reference was becoming slightly faster, but the branch mispredict was becoming substantially faster with every year. Now, something interesting happened in around 2000. In 2001, we had the last improvement in main memory reference time. Since then, up until today, it takes around the same amount of time, 100 milliseconds, to do a cold read from memory. For the last 17 years, a lot of things improved, but it still takes 100 nanoseconds to read an integer from a random location in your memory. Now, I'll be glad for this to change. I'll be glad if it becomes efficient, if it becomes faster. But it's unlikely to change because of physics limitations. What we concentrated instead is what happens here. L1 cache hit and branch mispredict. They were becoming a lot better. What it means now is every year caching becomes less practical than recomputation of the data. Because it's easier now to recompute. Our CPUs are faster. But the more data you store, the more likely you are to have it out of your cache, and more likely you are have to have a memory reference, which is not cached. And that's a tricky part, because in practice, when you're developing some kind of application, and you want to check if the caching speeds us up, when you're doing a benchmark, you have a very minimized workflow, very minimized workload, and it's likely that it will entirely fit inside the cache. It's likely that you'll never see this main memory reference overhead. It makes it really hard to figure out how to optimize software now correctly. And it makes it even harder because in what you're doing frequently is by introducing cache in one place, you're affecting the data which is used in all other places in your program. You'll be able to see this place speed up, but it will be hard to measure everything else slow down. Well, I have more bad news for you. In 2005 was the last time even L1 cache hit and branch mispredict improved. So if you see here from 2005, the next one is 2017. Since then, if you count in latency, it takes the same amount of time for us to do cache hit or branch mispredict or main memory reference. The CPUs, if you talk latency, stopped scaling for the last 12 years, which means that we can no longer rely on the CPUs to just figure out our performance for us. And that's why I'm giving this talk. So, yeah. The tricky part is, while it was improving substantially, you can see exponential speed up here in L1 cache hit and branch mispredict. We no longer can rely on it now. And if you're actually, this data is available here. I'll pause this presentation on the slide. You can roll through the years and see how these numbers change. They also include the network and the SSDs. The thing that changed over those 12 years substantially is actually the network throughput, network latency, and SSD throughput and SSD latency. Some stuff which previously was not meaningful to just store on disk, now it makes perfect sense. Some stuff which previously you had to do it on the same machine. Just spreading it across multiple machines was too much of latency, too much of waiting. Now you can do this. Now you can use multiple machines to cache the entire Scala ecosystem in memory, cache all the jars, and have perfect indexing. It wasn't possible 10 years ago. Okay, so what I was trying to make, the point that I was trying to make with the previous slide is that performance recipes do not age well. I'm giving you here adventures to show how fun it is, but in practice I'm not giving you a low-level advice because it won't withstand the test of time. What will withstand the test of time is the general idea. And the general idea is that the hardware, in order to become fast, for last decades, for almost the entire century, was doing bets on how you write software. In order to make the CPU, the memory, the hard disk fast, they always try to assume something about how you write your code. So they're playing bets which, if you play with them, you'll become faster. If they win, you both win. If they lose, you also lose because you become substantially faster, slower than if they didn't try. So several bets that they play are temporal, spatial, and pattern. The temporal bet is quite simple. If you used a resource, you use it again soon. If you use some memory, or if you read some data from disk, or even if you resolved a DNS address, if you'll do it again, it will be substantially faster because you have caching on multiple levels. In practice, if the extremes are first read of an integer from memory takes 100 nanoseconds. If you read it straight again, it will take microseconds. It will be instant. The longer you wait between the first read and the second read, the more likely it will go out of your multiple levels of caches. If you try it at the same moment, it will be in your register file. If you try it slightly later, it will be in your L1 cache, and it will be 10 instructions. If you wait till it is in L2 cache, it will be hundreds of instructions. If we'll build memory, it will be thousands of instructions again. So in order to write software efficiently, you need to be aware that you want to make sure that at every moment of time, you're reusing the data. When you first use it and when you last use it, you want to minimize the amount of time between those two. Okay, the next one is spatial bet, which is if you read some data, you'll soon read some more data around it. Again, it's represented on multiple levels. If you read something from memory, it's read on first in pages, which are 4 kilobytes in practice, then in lines, which are 64 bytes. If you read from disk, you're actually reading like 2 megabytes blocks at least, or for some SSDs now, so even 6 megabytes. So it doesn't make a difference for SSD whether you read 1 byte or 6 megabytes. And you can take advantage of this. You can align your data in a way which makes sure that the data you use together is stored together. It's in the same object. It's in the same array. Be aware of this. It makes it that your software runs substantially faster. And that's the bets which are unlikely to change. So to give you an illustration on this, it's a standard example which is used in computational mathematics or in physics simulations. If you have a two-dimensional matrix, in our case, two-dimensional array, and you want to iterate over all the elements, you have two ways to do it. You can either have the inner loop iterate over the inner index or the outer index. The difference will be that the way how this is stored in memory, this version will jump element by element by element by element. This one instead will randomly read elements from different arrays. In practice, this version used to be 3 times faster, up until Skylake. At Skylake, they figured this out, and they made the CPU aware of this pattern. Starting from Skylake, you need 3 dimensions to see the thing. But the entire idea still applies. Make sure that the data you use is placed together. And that's a pattern match. So at Skylake, they learned the pattern of organizing arrays, that if you go through this indirection repeatedly, they may be aware of it. So the pattern bet is, they want to figure out that the patterns which your program repeats, and they want to bet on the fact that it does it all the time. And the most common one is the branch predictor. So if you take this example of code, this cycle for an unsorted array executes around 6 times slower than if you would have sorted this array before. And this is because if you sort this array, this if will first always fail, then will always succeed. And that's a common trick used in multiple areas of software engineering. Game developers, when they develop entities in their simulation of the world, frequently sort elements by type. This is because on every frame, all these entities have to update their internal state. And it doesn't matter in which order do they update it. Something else figures this out. If you sort them by type, then you have similar entities doing similar work one after another. And in practice, again, it introduces a substantial speedup. Another example and another way to explain a branch predictor, which I liked a lot, is the train switch. So you can think about the CPU as a train, and the branch is this turn. It either has to go left or it has to go right. Before branch predictors existed, the train had to stop in front of this crossing and go and make sure that the turn is in the right direction, and then continue. Stopping the train takes a lot of time, takes a lot of effort, so instead they did a bet. Now, if the train is a CPU, it will continue going through the turn. And if it makes the wrong turn, it has to stop, go back, change the track, and go again. What it meant is that if the CPU does the right choice the most frequently, you don't have to pay the cost of the branch at all. You just continue execution. But if it frequently loses your assumption, if it frequently cannot predict it, you have this branch stalls where the train has to go back, change the track, and maybe there is another train coming behind it, which also has to stop. That's what you should have in mind every time you write virtual dispatch in Scala. Virtual dispatch is this crossing. If in virtual dispatch you have the pattern which is tricky for you to figure out, it's likely that the VM and the CPU won't be able to figure out either. So all of this is interesting. Now, let's say you made a change in your application. You measured it. The application became 5% faster. Should you be glad? So the picture becomes even more funny if you take into account the recent findings for optimizations. These particular optimizations are for GCC because they're easier to model. So the figure 2, what they did is they took several real-world applications. The most commonly known will be GCC, BZIP, and H264, which are compiler, archiver, and the encoder, and they randomly reordered function in the binary. This blob of measurements are different speedups or slowdowns they have observed. What more or less it means that, if you take BZIP, there is, if you just sort the functions alphabetically, you get a speedup. For some applications, if you sort them alphabetically, you get a slowdown. The point that I'm trying to make here is that if you made some refactoring in your program, it can become faster or slower, not because you made something smart, but simply something about the layout may have changed. And if you're seeing the changes in this 10% area, make sure that you're able to not only reproduce them, but also to explain them. It may be that you're just seeing this reordering. This one is even funnier. The second one. That's the same applications, the same speed, but not reordering the functions, but changing the size of the Unix environment. When you start the application, the starting offset where you load the executable code depends on how many variables you have. In particular, one of the variables is the folder name. So what this graph more or less says, that for some applications, this IBM, moving it around the folders may change the performance by 20%.
It's a feature, don't worry about it.
Yeah, and you have to pay our support to tell you the right folder name. That's a paid option. And if you have an unsupported folder name, yeah. So in short, every time you're doing benchmarking, be aware that there are a lot of moving parts. You would try as hard as you can to eliminate them. There is standard knowledge about disable fake multi-threading, disable overclocking and downclocking. But the general rule is more powerful. Try to make sure that everything, as much as you can, is the same. It's run from the same partition, in the same folder, from the same user, with same environments, in the same bash environment, in the same shell script around it. Try to make sure everything is the same. Because, yeah, it influences it a lot. Just because you're trying two versions of the same application and you're seeing that one is 10% faster than the other, you may simply be benchmarking this difference in the folder name. If you want to, that's actually a very interesting paper. So if you want to read it up, there is this paper about producing wrong data without doing anything obviously wrong, which was published several years ago, and it includes more detailed findings about this technique. They actually have a follow-up paper which creates a tool which allows you to not fall into this pitfall. The problem is the tool doesn't work with GT languages, so it doesn't work with Scala. Okay, so the general advice. Getting performance is hard. It needs a lot of exploration. If you're trying to do small amount of effort to figure out performance, you can just get lucky and get a random sample, which happens to be lucky. You don't have any guarantee that your users will have the same sample because maybe they have a different username. You have to repeat these explorations. If you have know-how, which is several years old, it's very likely that it's outdated. If several years ago you used to have use some stuff stored in the database, some stored in cache, something recomputed, it may make sense to reevaluate your decision. And if you see big companies, let's say Google or Facebook, 5 years ago it wasn't clear for me, why do they reinvent the same thing every 5 years? Every 5 years they have a new database coming, every new implementation, this big table and other versions which re-implement something that existed before. It actually re-implements it with different assumptions. It makes perfect sense to do it. Because if you did something 5 years ago, it's likely that by the time the thing matured, the choices it did are already outdated. So the next one is that losing performance is very easy. Because these small things, as in adding or removing line in a cycle, may impact your performance substantially, you better start tracking performance early. Because otherwise, you won't know how did you lose it. How did you lose it? So my advice is start tracking performance from the start of every project that you do. If you have some project that you're working now, if you want to make sure it ever becomes fast or stays as fast as it is now, better add some performance measurements. And also, when you're doing these performance measurements, measure on a machine which has a reproducible environment, which has the same libraries, same username, same folder name. Make sure that it's the same every time you run it. Sometimes it may require you to run it on the old hardware. So to give you an example, Dart benchmarking scheme runs on a bunch of Pentium 4s because it was easier for them to make sure that Pentium 4s didn't do any tricky stuff or any smart stuff, and they stay the same. Whatever hardware they choose now will be already updated 5 years from now, so why not choose something which is already outdated? Okay, thank you very much. I invite your questions, and I'll publish the presentations and you'll be able to follow all the links and all the base data in this talk. Thank you. Do we have a microphone? Okay, I'll repeat your questions.
Do you think it will become more and more reasonable to measure energy impact of algorithms? So how fast is it? How efficient is it? And how much power do you use?
Okay, so the question was whether it will become more and more reasonable to measure the energy impact of algorithms. Did I get the question right?
Yep.
Okay, so I'm not an expert in this area, so I'm reproducing based off what I've heard from others. But as far as I know, the best way we have to make an application consume the minimal amount of memory is what's called race to sleep. As far as I know, we haven't been able to produce a CPU which, for substantial amount of time, consumes small amount of energy while giving decent performance. What we can do instead is we can have a powerful CPU which wakes up, does a lot of job, and then goes to sleep. So based on my knowledge, and I'm not an expert on this field, performance and power efficiency ends up being the same thing. You want to make sure that you can process your work fast so that the amount of time you have your CPU consuming a lot of energy is minimal before it goes to sleep. Thank you for a wonderful question. Yes, please.
How about virtual environments, like for example Docker?
Okay, the question was about the virtual environments, for example, Docker. So I'll give you the general answer, and please tell me if I didn't cover your specific question. So the virtual environments still use the same hardware. It still uses the physical CPU. Virtual environments make it hard for you to measure and benchmark, but the idea how to write software stays the same. If you want to make sure that your process you use are fast, you still use the same techniques. You may be interested to make, if you have a low latency application, you want to make sure that another virtual machine doesn't steal CPU from it, and then virtual environment may not be a good choice for you. But as far as writing the code, I think they don't introduce much difference, but they really make it a lot harder to measure. So my devices measure on the physical hardware and then run wherever it makes sense. Docker is a very nice isolation strategy, so it may make sense for you to simply run Docker and make sure your entire Docker machine has provided CPUs for it and doesn't share it with anybody, which will make it easier for you latency-wise. But performance-wise, I'm not aware that it introduces substantial differences. There are other things which I didn't cover in this talk, in particular the way how file system works. Docker has a very funny way of organizing layers in the file system, which almost nobody else uses. So you can end up having funny behavior in this area. But otherwise, I don't see why it will make a difference. Did I cover your question? Thank you. Any other questions? Okay, I guess everybody is eager to go and have some food. Thank you for your attention. Enjoy the conference.